Oh, I think this is working. Hello, everyone. How's the audio? Let's see. Okay, cool. So let's start. Thanks, everyone. I get into it quickly. This is going to be a long video, and I'm sorry for those of you who have to suffer, but for future people, they can watch it on higher speed. And so this is a talk that I want to talk about what I've been thinking about file formats, the engineering parts, and not the politics. For politics, you can watch my previous 3-hour video from last year, and that also explains why this work has not been done for the past 20 years. But in this talk, I want to focus on the technology. So, and I have a bunch of technology here wired up together from a tablet via Google Meet, going to the cloud and back to the computer and then broadcast here. So let's see how it works. Oh, no, that was fine. Okay. Oh, and before that, you definitely want to switch the YouTube quality setting to the highest in the office. I think it's 1080. The slides will work much better that way. So there's 3 parts to this talk I want to talk about. I call it part 1. I call Boolean expansion. Part 2 is called better ergonomics. And part 3 is beyond emulation. That's also partially why I call this better font formats, not format. The first part is purely about expanding what we have right now. And I keep talking about font format without defining it very well because I don't refer to any particular format. It's not open type or open font format or Apple True type. It's the combination of all of this, which is what's in circulation today. Like on Apple platform, you get a slightly different behavior than on Windows, than on the free platform, which is Hartford and free type. So I will refer to this common font format or dominant font format, which is based on a design of tables. The font is a bunch of tables. Each table defines or provides some data. And so part 1 will be about the kind of expansions that we can make to the font format to address immediate pain points in the industry. Part 2 is about switching our font formats from the specification and design, like from the source format to intermediate formats to the delivery format, switching all of that to be based on a language that is specified using schemas, so we don't have to constantly write reader and writer code, parser code. So that's more like sharpening our tools. So part 3 is what I'm personally most excited about, and that's the part that I'm having a longer term vision, like a 5 to 10 year plan, and that involves adding general computation to fonts, and I get to that soon, or maybe in the second hour. Part 2 is going to be really short, like maybe 2 minutes. Part 3 about 15 minutes maybe. Part 1, or longer. Part one is I'm going to get into details of a lot of pretty much touching every piece of the current font format. And just to make this more accessible to both type designers and to general developers, I'm going to explain a lot of things or introduce the problem, introduce the current table format, and then highlight my suggestion for how to change it, with going into just enough detail that those of you who are font format hackers can have a meaningful conversation with me. So that's the plan. And then part one itself, a lot of it involves what I call upgrading font variations to a 2.0, if you wish. Is significantly enhancing the variation model. So I will, since variations are the hot topic in fonts, they're only 5 years old, I'll allocate more time on that. So part one, boring expansion. So there's multiple problems I want to try to address here, and these are problems that have accumulated over the years. And before I start, I want you to I want to give you some perspective about how stuck or how stagnant font formats have been. Basically, the fonts of today, skip for variable font, forget about variable fonts, like is non-variable font, TTF, OTF. The format that specifies the glyph outline hasn't changed since the late 80s or early 90s. The shaping hasn't changed since late 90s, early 2000s. So if it was any other aspect of computation, it would look really hilarious to you if, for example, we were still serving web pages from IIS servers on Windows NT, or if we were still using GIF images for everything, for photography. That's how stagnant font formats have been. Even the font variations work that we did in 2016, we just imported the model from Apple's 90s technology without rethinking it or expanding it, really. We just expanded it to fit into OpenType. We didn't touch the model at all. So that's how stagnant it has been, and that's why there's so much work to do, because we've basically missed 20 years of time, and we have missed 20 years of collective computation learning. And that's more the focus of part three. But for part one, I want to enumerate a bunch of problems that we are trying to address. One, fonts right now have a 65K limit on the number of glyphs, so glyph count. This comes simply from certain fields in the font format having been 16-bit numbers from the 80s, 90s, and it was never changed. And 65K might sound a lot and might sound more than enough, but as many of you know, it's not even enough for one full CJK font, CJK being Chinese, Japanese, Korean. And then when you get to fonts like the Noto Font project, Noto fonts, for those who don't know, Noto is the default font on Android for most scripts that is other than Latin and Cyrillic and Greek. So if you're reading, writing Arabic or any of the Indic languages or Chinese, Japanese, Korean, that font you see is the Noto family. Now, because of limitations in the font format, including this one and many other limitations, right now Noto is divided by script. So there's Noto Sans Arabic, and then Noto Sans Devanagari, and then Noto Sans Thai, and there's over 100 different scripts, and each of them end up being a different font with a different font name, and this has its own problem. When you get to serving them as web fonts is problematic. Enumerating them in applications is problematic. There's real pain in not being able to have one font that is called Noto Sans and have it work everywhere. So that's one of the things. Again, this limitation has been known forever. Everything I'm going to talk about, most of these are not new ideas or new problem statements. They are widely known in the industry. It's just that there has been no effort to actually address them. And I think I have worked out a full set of proposals to address all of these. So that's the 65K limit. Another issue is, uh, let's call it smart components or just better components. Uh, as we will see in font design, there's a lot of image or shape sharing. For example, if you have an A with an accent, ideally you want the font to know that this is the same shape as the A itself, and there'll be some sharing. Now, font designers have been designing like this forever. Newer font editors also allow for something called smart components. It's components that are not just static, having one shape, whereas sometimes they can be stretched or depending on the uh, constraints or be taller or smaller. So the components themselves have some variation. And we want to introduce that into the format. It addresses problems with CJK design, like Chinese, Korean, and Japanese fonts can become significantly smaller if smart components are available. And then there are other things we will address while changing that. We will better variation, better transformation. Well, basically, as we will see, all of the 3-4 problems I'm trying to address, they end up touching the same parts, the same multiple parts of the font format. So while there, we will address many other small things as well. The thinking being, if you have to change the rasterizer, if the font that using new features won't work on old systems, which is a reality, then we might as well address as many things as we want, because the next opportunity to make such a breaking change will not be in another 10, 20 years. But I will get to a point that I'll make it clear this is not what I'm actually doing. I'm not going to propose a font format that then every new font has to be created in the new one and the old one. I'm offering continuity to for future proof the file format, whereas for small fonts, for fonts that don't use the new features, they still will be distilled into the same existing format. So smart components, and then better variations. As I said, I will focus on that a lot. And then there's better shaping or layout, as let's call it for now. And that's pretty much it. And well, let's also put better outlines. Well, between this, that's addresses all the different aspects of the font and the font format existing today. So now, the way we are going to change this, I want to share or briefly discuss some design principles that I've been using to guide this work. Well, the main design principle for the whole work is really Japanese wabi-sabi, but I don't want to get theoretical about that. What we are doing is a few points to keep in mind as we discuss different designs. I want backwards compatibility to be the natural state. That is, what do I mean? For example, take the 65K GID limit. So there's a lot of, when we say GID, that's just glyph ID, glyph identifier. So that comes, where does that come from? That comes from a lot of 16-bit numbers in the font file. So one would want to say, oh, let's just add a 32-bit like version of the tables, and then that becomes the new format. But even if we do that, we will notice that using 32 bits all the time is a waste. And font binary sizes are important, like whether it's serving over the web or to mobile devices or shipping them on small devices like cheap Android phone. Font file binary sizes do matter. So this gives us an opportunity to update the font format to allow more than 16-bit numbers, but in a way that the 16-bit existing 16-bit mechanism is the natural, more optimized way to encode fonts that don't go beyond the 64K limit. So that's the design principle I want to uh, keep working with. Another way to think about this is how the PC, personal computer, evolved from an 8-bit architecture to a 16-bit architecture to a 32 and 64, and Windows evolved with it, still being able to run older binaries for a long time, like 20 years or so, before they decided to remove some of that. So that's backwards compatibility at natural state. Uh, that said, it doesn't mean that we are not going to change non-backwards compatible optimization when necessary or when justified. So, for example, there are certain pain points in the layout tables that make compilation of fonts hard. We know exactly what they are, why they are, and we can introduce new ways, better ways to do the same thing. And then the font compilers we built can have the option to generate only using the old legacy font format parts or the whole new things. So another way to think of this is, again, if you look at HTML, CSS, the web APIs, the web platform, that's a good way how things can change while still not having to throw out everything all the time. And then transients, again, the 16-bit to 32-bit is a good example. Note that we just need to update the font format to buy us time for another 10 years while we build the next generation font format. So we don't need to update the common font format right now to be like good for forever. And then imperfection, you need to get comfortable with it, because what we have as the font format currently is messy. It's very messy. It's ugly. It's a 30, 40-year-old persona. It has scars. And what we end up with updating it cannot be nicer than the original. It will be in some, but you have to adjust your sense of beauty and sense of design to be able to see beauty in updating and working with the broken stuff we inherit. And finally, or before finally, harmony just meaning that when touching certain parts of the font, it's preferable, we prefer like designs over anachronistic designs. So if you're touching the glyph table and the glyph table is using a bit code schema, it's preferable to use similar schemas to extend it as opposed to, say, introducing a stack machine. When working in the CFF part, if we work in the CFF part, that's using a stack machine is preferable to keep the same style. So basically just saying that keep the same style. And finally, liberation. That's the overwhelming theme of part one. As we will see, a lot of the pain points in the font format are from self-inflicted limitations. And we can address the pain points by just relaxing the limitations that do not serve us anymore. Uh, let it. So we're going to make the free the file format, and we will see how more expressive and less painful that will become. And then it's focus. We're not. I'm not trying to address every problem or every limitation of the font format. That will be addressed by part 2 and 3. But right now, I'm trying to address the pressing needs and pain points of the industry. And I've got to say, Google Fonts team has been asking me to come up with a plan to address many of these things. And I'm finally happy that I have a coherent proposal that addresses many things. So that's why I was so excited to share this with you. Okay, so now how do we do this? Sure. So 64, 65. So currently there's a limitation in the font format that a font cannot have more than 65,000 glyphs. And this limitation comes from two parts. One is, well, the second part is that glyph indices in a lot of places are encoded as 16-bit numbers, 16-bit unsigned numbers. But part one is that the number of glyphs in the font isn't specified as a 16-bit number. So this is a uint 16 in the, and the number of glyphs in a font is specified in a part of the font called the maxp table. And maxp stands for maximum profile. So this is the realization and the constraint we are going to free. One, there's significantly, surprisingly few places that this maxp number of glyph numbers is referred to in the font format. 3 or 4 is all I can count, and we'll see how to address most of them or all of them. 2, another realization is that even when the maxp num glyphs number is referred to for rather anachronistic reasons, it has been re-specified in that part of the font. It's encoded again with a constraint requirement written that this must be the same as maxp num glyphs, which is stupid, right? If you're referring to it, then why encode it again? If you're encoding it again, why require that they be the same? So as we will see, this whole limitation is self-inflicted and unnecessary, and we can remove it with surprisingly little pain. And then the GIDs are 16 within a lot of places. As I said, we're going to add bigger structures that allow access to GIDs beyond 16-bit, but the existing ways to access GIDs will also remain as part of the recommended format as an optimization. And just true to my design principles and file size saving, I'm not suggesting that we go all the way to 32-bit GIDs because I don't think that's necessary right now. I'm suggesting that we go to 24-bit GIDs. And the reason here is important. It's not that I have any problem with 32-bit GIDs. It's just that for file size saving reasons, I want to have the 24-bit version in. And then if we do have the 24-bit version, which supports up to 16 million glyphs, then the question is, do we really need the 32-bit version in the next 10 years or 20 years? And I think the answer is no. So while adding the 32 bit is really easy. It will be yet another template instantiation in our C++ code. For the sake of like reducing complexity, I'm not proposing that. So now let's look at where we need to make changes to allow to go beyond the 64K glyph limit. So as I said, the max speed table has a num glyphs in it, and this is typically exposed by various APIs as the number of glyphs in the font. So but those who know the format deep enough know that already in some tables like the G subtable, you can access or produce or output glyph indices that are beyond the num glyphs. Any 16-bit number you can actually produce. What happens with it is unspecified. So, but there's a actually unwritten assumption that the font is a collection of glyphs, and such glyphs are addressed from 0 to num glyphs -1. So we are still going to keep that. However, again, I want to free the format. We're going to say, oh, any glyph ID, any 32-bit unsigned integer is a valid glyph index. It just happens that most glyph indices produce empty glyphs. An empty glyph is something that draws nothing. And that's a very well-defined way to expand the glyph space to be the entire 32-bit address without constraining what's valid and what's invalid. So in the existing font format lingo, glyph indices beyond the num glyphs are sometimes called virtual glyph indices. We're not going to call glyphs virtual and non-virtual anymore. A glyph index is a glyph index, and it can be any number. Most fonts don't encode anything for the higher up numbers, but we're going to stop talking about legal and illegal or virtual and non-virtual. So the num glyph in maxp is a still 16-bit number, and we leave it that way for legacy reasons, and anywhere in the font format that refers to that number will continue to use that number. But as we will see, we make a lot of the few places that use this number, we're going to remove the requirement. So how does that work? Well, let's talk about the glyph outlines, the shapes. The shapes themselves in the current font formats quickly talking about like the current font formats, open type, open font format, whatever, have two different ways to encode glyph indices. One is called the true type style, and this is in the GLYF table, and then the CFF or postscript style. This is in the CFF and CFF2 tables. And for those of you who don't know the background, the CFF stuff comes from Adobe. The true type stuff comes from Apple. The true type stuff is the most common way, like that's the format that most fonts use. The PostScript CFF style has certain advantages like using cubic Bezier. So in my proposal, we're going to keep CFF2 as legacy, and we are going to expand the true type model. Let's see. Okay, so the glyph table, the true type outlines are specified in a couple tables. One called Lookup, which stands for location, and then the glyph itself. So Lookup is really just an array, just an array of offsets. And these offsets point to the glyph table Each of them is the start of a glyph in the glyph table. And so there's a requirement written in the font specs that the length of this array must be max p num glyphs plus 1. But as you can see, the length of the array is also, you can deduce that from the length of the binary table itself, because the length of the table is also specified. So this is one of those redundancies that the spec requires that the length of loca should match number of glyphs in the maxp table. Let's just remove this requirement. Well, the length of the loca table tells you how many glyphs have shapes defined for them. And this is the offsets in there already are 32-bit. They have the 32-bit option, so there's no problem. So already by just removing that one-line requirement, we allow specifying shapes for arbitrary number of glyphs without any change to the format. So that's the kind of thing I'm talking about. Now, such glyphs, if they are composites, composite glyphs are glyphs that refer to other ones as components. Now, the composite format still uses 16-bit numbers to refer to components, so you still cannot build composites out of the higher up numbers. But for that, we need an extension. So that is one of the things we address when we define the new component format. But already, you can do a lot with this. And the nice thing about it is, if you build a font this way, all the rasterizations, we just ignore the extra data in local glyph table, they can still access the lower 65K glyphs, but not the higher up. So this is very similar to how the PC evolved. If those of you who remember 286s and then 386s, and then initially memory was 16 bits, so then it was segmented, and then 32-bit memory was introduced as a protected mode. You had to opt in, and then there was high mem and low mem, and so it's very similar, which makes sense. They both are evolving from the same roots, which is the PC of the 80s and 90s. So that's for the glyph outlines. Another thing we did just by this is that we made add using a new glyph index, a new glyph ID free. One of the problems with the true type glyph table model is that if you want to use components, if you want to build your composite glyphs out of components, each of these components have to be allocated a GID, a glyph ID, and then all the 3-4 tables in the font that must have data for every GID have to add data for them, even if it's irrelevant to that component. So we're going to address that as well as by removing restrictions. So we want to make it such that allocating a GID becomes a free operation. There's no bytes added to the font to just declare a GID legal. That was part of the distinction I made. So basically, the local glyph, any GID that is not addressed here, simply doesn't have a shape. It might be used for other things, but just doesn't have a shape. So this is, I like to call them enlightened components or free radicals, as we will see. So that's for the glyph outline. So glyphs also have a declared width. That's called the advanced width. So if this is glyph, typically there's a width that says, okay, this is my natural width. And that width is stored in a pair of tables, the HA and HMTX. HA standing for horizontal header, and HMTX is horizontal metrics. And there's similar tables called VHA and VMTX for vertical metrics for use for vertical typesetting. And we don't use vertical typesetting for Latin most of the time, but the East Asian scripts rely on it heavily. So these are stored. HMTX, again, the way they are stored. I'll focus on the horizontal one. The vertical are similar, literally similar. So the HA table just has some header information, and it has one field that is relevant to the how the HMTX is interpreted, or one or two. But the point being that the HMTX, again, is an array. It's just an array that has the advanced width for every glyph, starting with GID 0, GID 1. It also has a number called the left side bearing, but left side bearing is something unused. It shouldn't have been put in the font. We're going to remove it where we can, but we don't touch the existing font structure. So basically, the advances are specified one by one, and then there's a cutoff point. Again, this was done to optimize for fonts like CJK, Chinese, Japanese, Korean, where a lot of the glyphs have the same exact width. The cutoff line is specified in the HA table, and anything after the cutoff line doesn't have an advance specified. It's just that the advance of the last specified advance is copied in. They still specify the LSB for all of the other glyphs, and as I said, LSBs are not necessary for the function of the font, so we're going to remove it when we can. But the point here is that, again, the lengths of these arrays are deducible independent of the max p num glyphs, even though the spec says that the number of these rows should match max p num glyphs. Just removing the requirement, again, we get a format that can specify more. Now, there's a disconnect here. The first max p number of glyphs, we will keep the format as is. What we are doing is, for glyph indices above that, we just put them here, only the advanced width. So again, this to existing rasterize, this part will look like extra data at the end of the table. To newer rasterizers, they know that it's the advanced width of the glyphs higher than num glyphs in maxp. So again, removing a requirement, freeing the format. So any glyph that is not listed here just doesn't have an advanced width. It has an advanced width of 0. So these two changes already give us a lot. And this, I can't claim to have addressed anything unless I also address the CMAP table. CMAP is where Unicode character code points are nominally mapped to glyph indices. So when you say type A in a computer, that's represented as Unicode code point 41 or 41, that's a hex number. And this is a notation, U plus. This is the notation to specify a Unicode code point. When you get to a font, the first thing the font does in using the CMAP table is it says, oh, U plus 0041, I use GID 10 for it. That mapping is in the CMAP table. CMAP has a lot of legacy stuff, but the nice thing is it also has a format 12 subtable that already uses 32-bit numbers for GIDs. So we got lucky there. Basically, it has 32-bit Unicode code points and 32-bit GIDs. The reason it was done is that back when format 12 was being added, some people thought alignment is a requirement, so they didn't want to pair a 32-bit number with a 16-bit, so they made both 32-bit, but that works to our advantage. So CMAP already works. The format 14 and format 14 needs an update. Format 14 is a subtable in CMap that can specify Unicode variation sequences. That one uses a 16-bit GID that needs to be updated, or unless it can only access a lower 64-bit glyphs right now. So that's CMap. So just these two tiny changes, remove requirements, we already can specify shapes and advances for this for fonts. What about format? I'm tending to questions. Format 17. Which one? There isn't a format 17. What's that one? Okay. Let's see how we're doing here. Oh, and while I'm at it, so I kept saying the LSP is unused and unnecessary. That's true for horizontal typesetting. When we get to vertical, the VMTX table is similar to HMTX in that it has what's called the top side bearing and then the vertical advance width. And the top side bearing is currently needed to derive what's called the vertical origin of the glyph. So glyphs are specified based on what's called the horizontal origin, which is baseline left, whereas for vertical typesetting, we need to know for each glyph where the vertical origin is, and the vertical origin is typically centered horizontally, but this height needs to be specified somewhere. Currently, the way it's derived uses the TSB. We don't like to do that. So CFF fonts already use another table called VORG for that, and I'm going to suggest that we use the same mechanism for TrueType for the future fonts, so we can remove a specifying TSB for higher glyphs. So that covers the basics of the font. We still haven't updated tables like GSUB, GPOS, more advanced typesetting tables also need to be updated. And yes, let me find that slide. Oh, these are my slides, by the way. Anyway, this is how old school I've become. And I was telling my friends that I got to the age that I ask a younger person to help me with my tablet. Okay. We're 45 minutes in. Let's take a 30-second break and I'll continue. Any questions so far? Okay. There's a question, very good question. Any reason for sticking with fixed with integers as opposed to variable length encoding like UTF-8? That's a very fair question and very good point. As I said, for this part of the expansion project, I'm sticking with the existing design of the font and the font format. as I said, when we get to part 3, I'll talk about my plans for freeing away from a fixed encoding scheme. So we'll add this there. Okay, let's continue. Let's quickly talk about layout tables, gdef, gsub, gpos, and then we move on to more interesting topics. So now we are going to talk about what's called layout, and that would be gdef, gsub, gpos tables. What layout means in this context is that, as I said, like the CMAP table says, okay, I saw a Unicode capital letter A. I know GID 10 is for that one, and I saw a B, and that's GID 11 and F. Well, typesetting is not that simple. It's not just putting one shape after another for per character. So that's where GSUB stands for glyph substitution, and GPOS stands for glyph position. That's where they come in. Okay, let me pause and check address chatting. So I want to be able to read the chat to see if I'm cutting off or I need to explain something more. So if you keep general chatting to minimum would be fantastic. But yes, there are a couple questions. I'll quickly address them and then continue. So Ken mentions that that format 13 CMAP table also uses 32-bit GID. Yes, that's correct. 12 and 13 both work. They don't need any change. And then Peter Constable observes that all tables have a 2 to the 30 limitation. That's also correct. Yes, as I said, we are not expanding over the full 32-bit GID. We're making, what I'm suggesting is making at least 24 bits of GID usable in every table. So those are compatible. And Lawrence Penny is asking, did you consider using FFFF or FFFE as here comes byte 3 and 4 of the GID? So that's another way of what Akhil had proposed, which is fixed with integer. Well, again, right now I'm not proposing a way to encode the GID because the way to encode the GID really depends on the context, which table you are touching, and different tables, different places invite different designs. So we get to that. It's not going, and yes, mostly we can't do that in a lot of places. And to answer Akhil's question as well, because fonts by design need to be random access by GID. You don't want to have to parse and process every byte to get to the shape for glyph a million. We want to have the random access by glyph index, and in a lot of places that means an array of fixed size GIDs, but we can have different versions of that array, a 16-bit version and a 24-bit version. That's how typically it happens. So yes, random access by GID is a requirement we need to keep. So what do GSUB, GPOS do? GSUB and GPOS. GSUB, you can think of it as it's this, say the glyph for F and then the glyph for I. It says, oh, I know I have a shape for just that, replace it with my FI ligature. So what typically you think of ligatures are encoded there, but there's also, when we get to scripts like Arabic or Indic scripts, or pretty much the vast majority of scripts in the world, all them, or at least half of them, require these kind of substitutions to work properly. You can't read if that is not done properly. Like, for example, in Arabic, being a right to left script as well, these are the Unicode letters for my first name, but the correct rendering of that is this very connected shape. So this is, let me switch color. So this is the first one. This is the medial form of the second one. So this one is called the initial form of be, medial form. This is the final form of dal. And these two don't connect contextually, so they are called the isolated form. So these kind of logic is encoded in the G-sub table. And then G-pos stands for positioning. Again, another, so this was using the Naskh style of Arabic scripts. Another, like that stylistic style, would write the same thing like this. Or the word nastaliq itself would look like. So this is what some people call the cascading Arabic. The point is that the baseline, like the letters don't all sit on the baseline, whereas the last one in the cluster sits on the baseline, and then they just connect and stack up. And then you have to position these things, dots and the acrylic marks and other ornaments around it. So that is done in the position, that's called the positioning, and currently it's done in the GPOS table. Both of these uses table design that is basically a serialization format. You have a what's called a table, and typically that starts with a format or a version number that specifies the layout of the table, and then it uses offsets to other tables that use offsets to other tables. So a lot of byte sharing can happen through this offsetted design. Now, one of the pain points here is that most of these offsets are also specified using 16-bit unsigned integers, so they are limited to 64K bytes. That introduces a constraint on the font compiler that it has to order these objects, serialize them in a way that these offsets do not overflow. And that becomes a hard problem as the font grows. That's, for example, why we can't have easily all of the non-CJK Noto fonts in the same font. The sharing becomes really hard to sort out for the compiler. So while addressing the 16-bit GID limit, we also address the 16-bit offset limit. Basically, a bunch of the structs, we're going to add a 24-bit version of them. And whenever we talk about G sub G pods, expanding them, going beyond 16-bit GIDs, the first response is that, oh, but we have to duplicate all the dozens of tables in these tables. It's actually not that complicated. It doesn't, not every struct needs to be duplicated, and I'll show why. So the bulk of the there's a suggestion that the 16-bit file offset limit could be augmented by a file-wide multiplier, or in this case, I would take it as a table-wide. So we're still trying to not break the interpretation of any bytes. Like if you throw a new font at an old system that was written properly or is in common usage, there shouldn't be any byte of the font that they mistake for something it wasn't designed for. So basically, that's a awkward way of saying we want our changes to be backwards compatible, not in the sense that the font will work on older system, but it wouldn't be misinterpreted badly, at least. Again, we're not, it all depends on the context. Peter is asking for subtable offsets, would it be significant size saving to use 24-bit offsets rather than 32-bit? Possibly not. I mean, significant needs definition. The way I look at it is 24-bit offsets support up to a G sub G plus table of 16 megabytes. And I think that's enough. So the 24-bit offsets offer savings that 32-bit don't. So to justify doing 32-bit only and not 24, we need reasons. And well, mapping the match, like pairing the 24-bit GIDs and the offsets works very nicely. And again, I'll show exactly that adding one or the other becomes really a one-line instantiation of a template with a different set of types. But basically, yes, we are defining, you can think of it as defining a small, medium, and large version of some of the structs. The small one is the current one using 16-bit numbers. The medium one has 24, and then the large one has 32. Whether we add the large or not is something we can decide. And then the same also applies to the number of items in an array. So a bunch of the tables list encode arrays of things, and the length of this array is typically encoded as a 16-bit integer, and then we will add expanded version of those using a 24 or 32-bit. So there's three different limitations: the GID, the offset, and the array lengths. All of them have the same problem, and we introduce tables to address all of them. So the bulk of the data in G sub G plus comes in what's called lookups. And a lookup, internally, it has multiple subtables, but in the end, you get to lookup subtable. Most of them look like this. They start with what's called the coverage field, and then what we call a payload. The coverage is another table format. It has two different formats defined for it. It's basically an enumeration of a set of GIDs. So a set as in a mathematical set, like GID 1 and GID 5,000, whatever. So there's two different formats of the coverage table. Format 1 basically lists the GIDs. It's an array of GIDs, a 16-bit wide GIDs. That's format 1, and then format 2. Let's see. So format 2 is range-based. So it's also an array, but array of start end of ranges. So obviously, we just need to add 24 or 32-bit versions of these two, the single GID and then the range GID. The length of this array is also 16-bit. At the same time, we address the same again. So when we introduce a 24-bit version, both the array lengths will be 24 bits and the GIDs will be 24 bits. Same thing about 32. Again, now it's very easy to quickly get into this explosion of subformats. You can think of, oh, what about a short array of large GIDs or a large array of small GIDs? Well, we won't add an explosion of all the different options. And by the time I get to part 3 of the talk, you'll see why, because it's unnecessary in the long term. So by just updating the coverage table, you allow applying lookups to GIDs in the high range. And typically this payload is an array. For example, the coverage table might list the GIDs that the subtable applies to, And the coverage table returns a number called the coverage index. Uh, that's just the location of the GID in this array, in this set, and that index is used to look up the payload. So most of these subtables can still work without any update by the virtue of the coverage table allow specifying higher GIDs. So for example, the single substitute subtable, let's look at that. Single substitute is a kind of lookup, a kind of substitution lookup that replaces one glyph with another, just without context. It just says, oh, replace this one with this one, and replace this one with this one. And so it's basically a one-to-one mapping. The way it is done, as I said, is the coverage table. The coverage table says, oh, my input is glyph A and glyph B, and then the payload is a replacement. And obviously, there's also the format number here. I'm talking about, say, format 2, I think, which enumerates the replacements. The replacements are enumerated here. So, well, this one would be the length of the array. Well, so the length will be 2, and then the replacement GIDs are here. Now, as you can see, if these two use higher up GIDs, you still can substitute them as long as the substitutions are lower GIDs. But to enable accessing the higher GID in the substitution, yes, we need to bump the format, add a new format that, again, uses 24-bit or 32-bit, both for the array length and for the GIDs. So that's how we are going to address and offsets at the same time. Yes, even the offset to the coverage table. So that's what we are doing. And the total number of tables that need this kind of adjustment is not that much. It's not even a dozen. There's a single substitute. So in terms of substitutions, there's the single substitute, there's the ligature substitute, there's the alternate substitute. Alternate and multiple structurally are exactly the same. And then for positioning, there's again the single positioning, there's the pair positioning, that's where kerning comes in. And that's it. These are the main types that need adjusting. And yes, there's the mark attachment ones also need a bump to allow enumerating more. The biggest, the most complicated part of GSOM and GPOS are what called the family of contextuals. And there's 6 of them right now in each of GSOM and GPOS called optionally chained or not, and context formats 1, 2, 3. Two of these formats don't need a change because they just specify things with GID, with coverage table and class def tables, which doesn't need to be updated. The third one specifies, or I think format 1. One of them uses GIDs directly, so that one can be updated, but I'm not immediately suggesting that we do that because with a good compiler optimizer, most of the time we want to use format 2, which is class-based. So it's optional to upgrade that one or not. I also need to talk quickly about class def tables. Well, class defs are a sibling of the coverage table, whereas the coverage table encodes a set of glyphs, and well, it's a ordered set. It returns an index of the GID in the set. That's the output of it. And the way the spec is written, the the, the indices should be consecutive, and they should be sorted. The GID should be sorted. So basically, the coverage index of a glyph ID is its sorted position in the set. However, as a lot of places in the font format, this constraint cannot fully be enforced. For example, the format 2, which is range based, for optimization reasons, it has the start and end of a range, but also the start coverage number. Because if this number wasn't here, you would have to add up the length of each range before it. So this number already allows overlapping coverages for the same glyph. The class def, on the other hand, is a different structure. It classifies glyphs into multiple bins. So the API for this one is you give it the GID, it gives you what's a class number. Let's put it by K. And the classes nominally start from 0, 1, 2, 3, but there's no number. It's also another 16-bit number. The difference here is that multiple glyphs can have the same class number, and that's used in many of these tables to group, like to encode the payload for a family of glyphs only once. Now, one really interesting way forward, if we want to, is to merge these two structures. That allows for savings that currently we cannot benefit from, because if you remember, a lot of these tables have a coverage, the subtables have a coverage table and the payload, and by merging the concept of coverage and class def, we allow encoding the payload only once when multiple glyphs need the same data. So I'm not necessarily saying that we should do that now, but that solves a lot of problems. And then there's a bunch of other, so that's for the expansion of the 16-bit limit. And then there's a bunch of other miscellaneous layout work we need to do. And this is based on this is based on work that Martin Hoskin did. Martin came up with a list of things that, when added to the file format, will make things like graphite unnecessary. And Martin and I wrote a bunch of these proposals in 2016 for OpenType. None of them happened, but I'm reviving some of them and updating them for what I've learned in the meantime. Well, one of them, I'm just going to run through this, not get into detail. Lookup flag extension. This is one of the funniest ones. There's a field called lookup flags in the G sub G post table. It's a 16-bit number. It's running out. So the first proposal is to use one of the remaining bits to mean another 16-bit follows. So that's easy. There's one called glyph filtering. So currently, in the G sub G post tables, for example, imagine you are ligating F and I, but you want to write your ligature rule to work even if there's a combining mark in the middle here, like accent. So the accent can still, you want the ligature to form even if there's some other glyphs in between. The current format allows jumping over only glyphs that are marked as a mark. Well, the glyph filtering is just a mechanism to allow specifying arbitrary set of glyphs to jump over, because the limitation just doesn't serve us well and there's no basis for it. There's also the move lookup. So one of the biggest pain points in OpenType layout is that you can't move glyphs. That is, if in the glyph stream B appears between A and C, you can't just say have a rule that says, oh, just bring it here. This simple limitation is the cause of so much pain, and there's no good reason for it. Like, people will give you explanation, but none of those really explain why we don't have it. So adding it is a very simple way to make the mechanisms a lot more expressive. Um, there are other ideas we can use to reduce pressure on the table compiler, and a bunch of better, more optimized ways to specify things, but I won't get into them because it becomes really tricky over this format. So, and then quickly, let's cover color, and we are done with part one. Well, color tables, color fonts, there's 4 different formats of them in OpenType. There's the CBDT CBLC, which is PNG bitmap based. That's the one I designed. I suggest we call it Legacy because we also have the SPIX table, which is based on the Apple emoji color format. It also used to be PNG based. I suggest we expand it to allow JPEG X, XL. Yeah, I think so. That would future-proof the format to pretty much the best image compressions. And then there's the SVG. Oh my God, where do I get? I'm not going to discuss SVG. And then the last one, the fourth one, is what's known as the color CPAL. And there's already work underway to extend this table, this mechanism. It's collectively called the color V1 effort, and if you Google it, you will see it's something that I started based on need from the Chrome team 2 years ago, and then it handed it off to the some of the Google Fonts people, and then they're working with Peter Constable and Microsoft to add that to OpenType. And there's already it's very clear how to update that for 24 or 32-bit GID, so that needs to be done. This table is also where we started using 24-bit offsets, and they work really nicely, and we want to do that everywhere. The SPIX table is one of those that refers to max p number of glyphs without duplicating it. So the SPIX table, if it's desirable to be able to encode PNGs for more than 64K glyphs, the SPIX table needs a bump. But we'll see if that's actually needed, or people will switch to these other the vector glyph shapes for color fonts. Okay, so I think that concludes the 65K expansion project. What is left? I'm going to quickly talk about better outlines. Well, cubic glyphs. Basically, the glyph table, which is where the outlines are specified in TrueType style fonts, has always been based on quadratic Bezier curves. So this is a quadratic Bezier. And then the CFF PostScript tables have been based on what's called the cubic Bezier, which is higher order. These are mathematical objects, and this one, the cubic, is what most designers are familiar with, and it's more desired for design because it gives you different handles for the 2 endpoint directions, whereas this one is really painful to work with. The TrueType format, the glyph table, was designed based on quadratics because it was done in the late 80s and never updated. So there's been talks about adding cubics to the glyph table for years, and there's proposals. It's very simple how to do it. We just use one of the pair coordinate flags to say, oh, this control point is a cubic. So that works very simply. There's no aha moments or surprises, except for when you have 2 points, so-called on-curve points, and then you have multiple off-curve points. If they are cubic, the number of these must be odd, because every 2 of them offer one cubic curve with one implied point. So if the number is, sorry, the number of the off curves has to be even. If the number is odd, I've thought about how to use it for something. I don't like any of the options, so I'm just going to suggest we make that undefined or illegal. Uh, some of the properties I want to maintain is that if you reverse the order of the points, you want the curve to not change. So, for example, treating the last part as, differently would break that assumption. So anyway, that's a very simple thing we can do. I have ideas, hacks about how to make this behave kind of okay in older rasterizers, but I'm not going to get into that today. So that's the cubic glyph. And I think I've covered everything in part one other than the variation model upgrade. And is it okay? Let's take a 10-minute break and let's start again on the hour. Thanks. I don't know how this works. I'm taking a break. I just don't know how to update this counter. Technology. Let's see. I don't know. We'll be back. Okay. Do you hear me again, Esther? Okay. So let's just to recap where we are is part one, which is expanding the existing font format. And we covered many items, mostly the 16-bit limits. And then I'm going to talk about variations, basically variations 2.0. That's where we are. Lawrence is asking, did you consider encoding anything else with glyph flag bit 6 or 7? I'm thinking of curve order higher than 3, smooth, non-smooth. So the question is whether I considered higher order Bezier curves, higher than third degree Bezier's. I did consider, based on Lawrence's suggestion himself, I don't find them useful, and we should definitely discuss this in another meeting. I don't think it's necessary, and rendering them is just more work. Whereas by constraining to cubic and quadratic, um, cubics over quadratics offer file size savings, but if you go to higher order, unless designers also design in these higher orders, it's not useful, or you end up having to write really complicated polynomial optimizers to uplift from the cubics to the higher order. Anyway, I found it not useful. Again, remember, I'm trying to address the pain points that we are all sure of, and I'm not introducing anything speculative. Okay, let me pull up my notes. Okay, so open variations. For those who are not very familiar with this, so if you think of how fonts evolved from in the 80s and early 90s, fonts evolved from being bitmaps to being what we call a scalable or outline. So instead of encoding the specific pixels, they went to specifying an outline. And this outline is specified using line segments or curves. And these curves have, as we discussed, they're called Bezier curves. They are mathematical objects, and Bezier. There's different versions of they're polynomial, and we typically, so basically you can think of a line is a first degree Bezier. A quadratic one has one control point or corner, and it looks like this. That's a second degree Bezier or a quadratic, and the third degree has two control points or two handles. It looks like this. So the outline is constructed out of this, and then you can think of a zeroth order Bezier as being just a value, just a constant. It's just one point. This actually maps very well to the common drawing APIs inherited from PostgreSQL, which is called move to, line to, and well, curve to typically maps to the third degree polynomial Bezier. Some also have quadratic too. So these are the set of operations that these outlines are built out of. And so we upgraded basically from a fixed size model to a variable size model. So what font variations are, that's work that we as in like open type in general, like it was a collaboration between me and my team at Google, and then Microsoft and Apple and Adobe. It was based on ideas from the 90s from Apple and Adobe. So the idea is uh, going beyond a font file specifying one outline only. Basically, it was based on this realization that font designers for the past 10, 20 years, typically this is how they design a font family. They draw the what's called the regular. I'm not a font designer, you can tell. So you design what's called the regular, and then you design, this is the regular. And then you design, say, a black version, the extra bold, super thick. And then you also do a super thin or light. And then you can ask the software to mathematically interpolate between these to give you a light or a, what's other names? Or a bold here or a extra bold. So these are the ones that the type designer draws are typically called masters, though we should also find other name for that. So they might design these three, and then they used to ask the software to fill in the gap and generate, say, nine instances in total. And then one day I thought, well, this is stupid. We should just ship the originals and do the interpolation at runtime. And that's what variations enable. But while doing that, the variation model also doesn't stop at just weight interpolation. So the variations can be in any axis. The axes are referred to using four-letter tags. So this is the standard weight axis. And then there's also a standard width axis. There's also a standard optical sizing axis. Well, optical sizing basically refers to this concept that the font, depending on the size, is not just linearly scaled. It actually changes the form depending on the desired size. So these are some of the three of the main standard axes, but you can have arbitrary axes. And then the designers, this is called the design space. This is not like XY coordinates of the glyph shape anymore. This is the design space. And then the designer might design the regular here. They might design a black here, and then a stretched or extended version here. And then the black extended will be extrapolated basically based on the difference of the black and the regular and the expanded and the regular. It's filled in automatically. But if that's not desirable, if it doesn't look right, the designer can then add an extra master here to adjust it. And it's easy to imagine when you keep adding these axes, I can only draw up to 3 of them really. And then you start adding these masters, and then you have to update these corners to look correct, and then these things add up, and then you end up with a family that has something like 81 masters. That's like 81 different drawings of each letter, and that doesn't expand. It's impossible. It's very hard to design, to maintain, and the byte size, the file size just blows up. It's a combinatorial explosion problem. Now, this problem mostly happens because the axis that users find meaningful, like in this case, for example, the weight and width, are typically not orthogonal. Like, what do we mean? For example, a weight, I'm using the Noto Font family here as an example. The regular of Noto has a stem width of, I think, 96 units. And then the black has a stem width of 190 units. But as the width goes down, this is, let's say this is narrow, or then the regular might still have the same stem width, but the stem width of the black has to go down to compensate visually for the narrower font. So designers come to us and say, oh, I have a font that has this non-aligned design space. Well, the problem here is that the designer is thinking about the stem width, whereas the user is thinking about the perceived weight. In reality, the way they have to implement this using variable fonts right now is, this is your black, this line is black, this line is narrow. So you put the black narrow here, no matter what the stem width is. But then you have to add a master here because you have to fix up the stem width. So another way to say this is that the axes are not orthogonal. Like, changing the value of width, the width, the weight of the glyph shape also changes. Or another way to say it is that, well, so this introduces that explosion problem. Whereas, as some people have proposed, like David Berlow, you can design fonts using axes that are orthogonal. What does it mean? For example, you can have an axis that controls exactly the stem width, or even just the horizontal stem width, and another axis for vertical stem width, and another one for the true width, and another one for white space. And then the nice thing about these axes is that they are orthogonal, they are independent. So when you change the vertical stem width and you change the horizontal stem width, the extrapolated instance auto created here typically just works. So you don't need to add another master here. So this addresses the combinatorial explosion problem. Now, again, as I said, the problem is that the user desired axis, width, and weight don't line up with these axes necessarily, or they might be non-linearly and non-orthogonal, non-aligned related to this axis. So that's what that has been understood as the biggest problem with variable fonts since we introduced them in 2016, and that's what I've been talking about addressing in a proposal called Ar2. But since then, I have tried to address a lot other problems with pain points and problems and limitations with variable fonts. So I'm going to talk about this multiple set of changes that combined together bring variable fonts forward to a much more expressive system. So again, to recap, the problem with the current variation model is that the axes cannot interact in ways that we want. So the interpolation model in variable fonts is linear. Basically, the only thing you can do is to move points in a line. But it's called piecewise linear because you can add line segments, but there's no way, or there's no easy way to just encode a curve directly. That's also one of the things I want to change. Again, for those in the industry, you know that the underwear people, Akim and friends, found a way to work around this limitation, basically because Bezier curves are still linear in certain aspects, and that part gets mathematical technical, but curvature in the variation space, in the variation of shapes itself, has been so hard to achieve, and I want to make it very, very simple and natural. So that's another problem I'm trying to solve. And yeah, those are the main two. And then there's the usual limitations of offsets and sizes. If you want to declare 10,000 axes, it explodes. You can't compile the font. So free axis is also one of the things I want to do, to make a new, adding an axis free. Just declaring a new axis wouldn't have any byte size increase in the font. Same thing that I did with GIDs, I want to do with the axis IDs. And then also similarly, there won't be any distinction between a legal axis ID or illegal or virtual. Any axis ID you can encode is equally valid, although some of them might have no data attached to them. So the AVAR table, as I said, this piece was linear. So the API of variable fonts, the way they are perceived by the user of the font, and I'm not saying by the user of a design application, but the interface of the font, is that in the FVAR table, the font declares a set of axes, and it declares them with a tag, and then can attach names to them and other information, and then each of them have a range. It's a start or mean, minimum, default, and max. So these axis declaration together define that variation space that we talked about. Let me move this up. So, but to allow some nonlinearity, so this has mean, default, max, each of them. So to allow for some nonlinearity, the font also can have an optional AVAR table, and I don't remember what the A stands for. But what it does is that the AVAR table can apply one fixed function to the value specified by the user. So it can remap access to allow for some nonlinearity, but it has to be a piecewise linear mapping still. The problem is that when we say orthogonal, is that these two functions do not interact. The functions across different axes do not interact. So the Ar2 proposal is very simple. Basically, we want the output of each axis, the one that is actually used for interpolation, to be a function of all the input axes. So conceptually, this is very simple. And implementation is also very simple. We just put all these numbers into an item variation store, and we use a variation index map. So those are structures that already exist. We just repurpose them. So the AVAR2 table really will be 2-3 fields. It's so simple. It reuses the existing interpolation mechanism. So the output of any axis will be a full variable function of all the inputs, like any other variation we support. Now, one way to think of this is that you can still think of them as modified version of the input axis, but really there's no requirement. There's no requirement that this has to have anything to do with width and this with weight. What these are is up to the designer. So essentially, the public facing axis and the internal axis have different meanings, different spaces. But that's also an interpretation. You can think of them as the same, you can think of them as separate. The number can be different. Fortunately, FWAR table already supports hidden access. So if you want, you can declare all of them here and mark them hidden, but there's really no need to. You can refer to any access in by index and it will be valid. Uh, we get to that because the smart components are basically uh, going to use that, referring to individual access by index and modifying that. So that's the Ar2. Now, I want to talk about how we introduce curvature. So again, as I said, the underwear people, the amazing people at underwear, discovered years ago that by repeating the same axis tag multiple times, you can get higher and higher order Beziers in the variation space, even though none of this was intended by the designers. Uh, and there's no place in the spec that says the same axis tag cannot be repeated. So if you have a font that multiple times says wait, 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 then if you have three of them, then you can combine them and then you get cubic Bezier movements. It's amazing that non-mathematicians discovered this. Thank you, uh, underwear people. Uh, so first, I want to legalize this because it's already water under the bridge. So what I'm suggesting is that in the F4 table, we specify that if the same axis tag is repeated multiple times, they already end up next to each other because the list of axes has to be sorted by the tag. We will specify that at most one of them should be non-hidden. So these other extra ones should be hidden. And if there is any non-hidden one, that should be the first one. That's just to make it easier instead of having to look at all of them. Also, note that these multiple instances of the same axis tag can have different mean, max, and default values. There's no need to enforce to require that they have the same mean, default, max. So we shouldn't require that. Only one of them is public facing, so any UIs, the user of the font will only see the mean, default, max from the public one. The other ones are internals of the font and up to the designer. We shouldn't require that they all match. So this already brings in the hacky way of smoothness curves into the variation. Another, so we legalize this, but this is ugly. This is definitely not the way we should advertise building fonts. Another way we are going to introduce curves is that all of the variation data in the font are stored in only two places, two data structures. One is called item variation store, which I designed back then. And then another one is called the tuple variation store, which we inherited from Apple TrueType GX of the 90s. So this piecewise linear model of variation we copied directly from Apple's TrueType 90s technology and didn't extend it. We didn't try to address its limitations. So that's what I'm doing now. So all the variations are in these two places. And without getting too technical, the variations are stored as deltas. Each delta has this, what we call a support, or the part of the space that it is applied to, and then it goes, peaks to the top and goes down. This is what we call a tent. The tents are specified right now in those structures as a array of a start and peak and end for each axis, like one row for each axis. What this really means is that for each axis, we say, oh, my functionality for this axis is 0. When I get to a start, I start going up, contributing. When I reach the peak, I'm at my maximum contribution. This is value 1. This is the start. And then I go down and I go back to 0 at the end. So these start, peak, end values are specified for each axis. So even if you declare a new axis and nothing, no design in the font is changed, you automatically have to add a row here. And this is undesirable. So we just bump these two table structures to allow, well, a sparse a specification of this thing. So you just say how many rows you need, and each row now also has the axis index. So this is sparse. This is how we make the axis free. But by the virtue of specifying the axis ID, now you can specify the same axis ID multiple times, and you get the same higher and higher order Beziers without having to have the tag specified multiple times. So this is the second way we add smoothness. It's still based on the same hack that you have to specify the same axis multiple times to get higher order interpolation. We don't want to stop there. And this introducing curvature naturally is what I was struggling with. I couldn't fully sort it out, figure it out until I did on Sunday, and I was so excited that I scheduled this session to share that. So basically, the way our current variations work is based on this shape, this function. Like everything is built out of these triangles that have a start, a peak, and an end. So in mathematics, this is just called a basis function. You add up multiple, you add these up in different proportions to build any function you want. And it's easy to see why this shape was chosen by the Apple people, because if you have any piecewise linear function and call these numbers like m0, m1, m2, m3, 4, and this function is a function, just a mathematical function, then if you write this fx as a sum of mi multiplied by a function for each of them, these functions, the basis functions, all have triangular shape. So, for example, for this m1, the contribution of this one will have this shape. So this is the contribution coefficient of this point. What does it mean? What it means is that if you move this point up by 1 unit, then the function will go up by 1 unit here, but midway between these two, the function goes up only half a unit. And then anywhere before m0 or after m2, the function doesn't change. That's where this triangle shape comes from. It comes naturally. That's the basis function of piecewise linear functions. Now, it follows very simply that if we want curves, we need basis functions that are curved. And that's exactly what I'm proposing to do. In fact, I've sorted out the class of new basis functions that we need to add. Also note that this triangle shape, it has a start and peak and end, and it's, well, there's the going up side and going down side. Basically, it's a fixed structure using the function t. So Before start, it's always 0. After end, it's always 0. Between a start and peak, it goes up constantly at constant angle, and then it goes down at constant angle. So the true real basis function we are working with is t. This is not surprising because t is a linear function, is the basis function of all linear functions. If we add basis functions that are higher order, like second degree polynomial, third degree polynomial, we get curvature very easily. So this is the class of basis functions I'm proposing. We add two second degree ones. This is t square, and this one is t times 2 minus t. If you do this, then naturally you get quadratic interpolation, quadratic Bezier curvature in everywhere in the design. In the design space itself, in the mapping of axis, in the coordinate data variation. And these two numbers, these two functions are chosen to make it very simple. Like with my proposed changes, we add a flag field to every axis, axis used. So every time you are declaring one of these tens for each axis, you say which basis function you want to use, and you can specify that separately for the up ramp and down ramp. So with this, what we get is you can get curves that instead of looking like this, they can go up like this, come down like this. That looks ugly, is not very useful. However, the way this is designed is that if you look at the contribution, the basis functions of a quadratic Bezier, they actually look like this. One of them starts, comes down as t2, or 1 minus t squared. That's the same basis function as this one. It's the same. It's just flipped over. So it's the down ramp of this basis function here. And then the contribution of the third point is t squared directly. And then the middle master, the control point, has a contribution that looks like this. This is at half, but doesn't matter. If you scale it up, it actually is the same function as this one, going up and going down. So basically, what we get is that you get in a situation whereas current variation, you have three masters, and the path that they interpolate is this. You just change 4 bits in the font, and then it goes like this. It can pass through this, or it can not pass through. That is all up to the tooling. And then we also add third degree polynomial basis functions, and that allows cubic Beziers. And those ones will be just the T cube itself. And then the next one is also called as smooth step in OpenGL and other spaces. This one is 3T2 minus 2T3. Yes. And then the third one is TQ fourth minus 60 square fourths. Well, the details don't matter, but just to see. And these three, again, these are also called Bernstein polynomials in some respects. Again, let's look at the basis functions of a cubic Bezier. When you have a cubic Bezier, the 4 points, the first one starts at 1. The basis it starts at 1 and drops off. This is 1 minus, that's the one that is 1 minus t cube. Notice that that's the same down ramp of this function. And the last one starts at 0 and goes up. This is t cube as well. The middle two have a contribution curve that looks like this. For this one, for the first handle, it goes up like this and then smoothly comes down. I'm screwing up that shape, but okay, so the last one was easy. And let me change color. Okay. So the contribution of the first handle looks like this, and the second handle, it looks like this. Well, the way I've designed my system is that, and this peaks at, this is 0, 1, this is 1/3, and this is 2/3. They peak there. The way I've chosen my function, this shape as well as this shape are just this. And then this shape and this shape are just this. So you can still have a tent by choosing different basis functions for the up ramp and down ramp. You get the exact contribution you need to implement a cubic Bezier. So with this, again, you just specify this for masters, set the right flags, and it does the right thing naturally. And then the tooling can decide what to do with it. Like users might, it's hard to think of a master in a design space that is an off curve, but that doesn't mean that's how it should be exposed to the user. The tooling can figure out the math and produce the right, use the right basis function with the right multipliers. And then there's one last but absolutely not least basis function, and that's familiar to most of you, is the sine cosine, like the trigonometric function. All the previous ones were polynomials. This one is, in a sense, it's called exponential, but it's trigonometric. So this one simply is the sine function. It goes up from 0 to 1. And why is this important? This one is super important because it allows specifying rotations exactly, mathematically correctly. And that's one of the things we've been really missing. So yes, between this, like, so the line is its own first function. Let me just draw them quickly. So we have the first degree polynomial. The second degree has 2, which is this and this. And third degree, we have 3 of them. The smooth step. And then there's the trigonometric. So between these, 1, 2, 3, there's 7 in total. So each side can be specified using 3 bits, and we have 1 left. These upgrades variations to whole new dimensions. And one last thing, as you noticed, all of our basis functions now have limited support. They have a limited domain. They all start at 0 and end at 0. There's 2 ways I'm suggesting we change this. First, for the start and end, so remember, this is start, peak, and end. For start and end, we use a magic value in the file, which happens to be 80000. The actual value is not important, but we use a magic value to say there's no end, just stay there. So you can have one-sided things. That also offers file size saving and other advantages. So you can smoothly go up and stay there. You can come down. So that's useful, but I'm also proposing another mode that has no contribution at the middle. However, it has a start point and sorry. So this is the end and this is the start. So the function that this produces is it starts at -1, at a start goes to 0, then it goes up again. Again, these segments you can choose independently which basis function to use for. So, for example, you can have this. But what this is doing is that it uses the same master to have contributions on both sides of an axis. So if this is your middle, you can say this is my black, but you add this to get black, but also subtract it to try to get near the thing. And anyway, this is also useful, addresses many problems. Um, so yeah, let me check my notes. I think that's all about the variation upgrade. And then, yes, because of this cosine function, it also essentially means that we get a radial basis function interpolation, even though not with a Gaussian, with a trigonometric function, but that's not important. That's not a limitation. This is smooth enough. Okay. Yeah, I think that was all of the variation stuff. So it's 12:40. Let's take a, okay, Felipe says, since you can encode them with exactly 3 bits, do you consider using 4 bits so the fourth one is kept unused? Yes, what I'm proposing is that we add an optional 16-bit flag fill to each axis and then axis use. And then of the 16, 1 byte will be used 4 bits up ramp, 4 bits down ramp, the basis function, and then the other bits will be used to specify whether it's this kind of tent or whether it's this kind of tent. Oh yeah, there's also some extrapolation I want to do. The flags will be used for other things and some reserved, yes. Another thing I want to do is currently we don't allow extrapolation at the end of the space, but that's useful. So I'm suggesting if currently this end has to be after the peak and start has to be before it, it's very simple to define to say, hey, if end is less than peak, for example, this is peak. If end is here, then this is the desired function. It goes up forever. So this allows extrapolation. And we might want to do this with the trigonometric one as well, so it keeps rotating. However, I don't suggest we do that with the other polynomials because their numbers get up really quickly, and I don't think it's useful. I haven't found any use for it. So that's also extrapolation. And yeah, that was all for variations. That was also all for borrowing expansion part. So we are done with part 1. Part 2 and 3 are really short. Part 2 is less than maybe a couple of minutes, and then part 3 is more like maybe 15 minutes. So let's take a 2-minute break and start at the 45 after. And I'll read questions in the meantime. Okay, back. Audio good? Lawrence is asking, in Ar2, did I mean that design space locations are themselves delta by multi-axis variation? Yes, that's exactly. It will use a variation, what's it called? The item variation store with the unmodified input axis locations go in, produces a variation that is added to the axis. Yes. Peter is saying that trigonometric sine function we get a close approximation using fifth order polynomial. That's true, but since graphics hardware and CPUs and libraries have a fast implementation of trigonometry, I don't see any reason why not adding it, and it can express rotations perfectly. So I think it's a great addition. Okay, but the details, the details are all to be discussed and figured out. I want to put the ideas out. So let's get to part 2, and I have to rush now. Okay, part 2 is very simple. It's I said it's called better ergonomics. So what you have noticed by now is that changing the file format every time, we have to agree on the new structs and new structures and byte encodings, and then write them somewhere, and then encode this in different software like font tools and the Python font compiler tool chain, and then now there's a Rust ecosystem for font tables, so that also needs to implement it. And then we have Harfbuzz and free type, the free stack, and then a whole bunch of fringe implementations. And it's just, it would be so much easier if we didn't have to write parser code, reader and writer code for every change. And surprisingly, that's not a new idea. And there's a lot of ways to do that. The one I'm proposing is to use flat buffers. Flat buffers is a serialization format developed by Google and used by many, including Facebook on their Android app. Flat buffers, you can think of it as something better than protobuf, in certain ways, in ways that we need them. So what flat buffer, the basic idea here is that we can write schemas, we can write a machine readable specification of the font tables, and then automatically generate a reader and writer code from it. Flat buffer has very nice properties. It's very low overhead. It's lazy parse. You don't need to parse the whole thing into memory. It just accesses tables directly. And then the part that it really I love is that one of the challenges we have in font file format design and any format design is that you have to you want to add ways to encode things more efficiently using fewer bytes, but that the way we do that is adding more and more special cases, like for 1 byte, 2 byte, 4 bytes. This explodes the implementation. The implementation cost goes up as byte size savings go up. Flat buffers handle some of that for you. If, for example, you have an array and all of those are a small integer, it automatically uses the narrow encoding of those integer array. So we are separating some of the encoding optimization and figuring out the order of things from the actual parts that we as font engineers care about. So another way is we are leveraging existing work, and it just reduces the work that we the type people, the font engineering, the font hacking part need to implement on top. So what am I suggesting we use flat buffers for? Well, right now the sources for fonts, the common format, the common open format is called the UFO. It's based on XML, comes with all the problems of XML, and it uses one file per glyph to store the outline, and reading that has been painful. Reading XML is slow, and then it's just a pain. Moving to flat buffers, there is a very natural option, and then there's this intermediate format we have in font tools called TTX, another XML format. This one, so whereas the UFO is a source, it reflects the designs that the designer had in mind. The TTX reflects the tables that go with the binary font. It's just it's just in an XML format. So it's the XML representation of the font table itself. Uh, Again, we can use flat buffers there for uh, to solve some of the main intermediate problem. What do I mean by intermediate? When we are going from the UFO sources to binaries, be it OTF or whatever, uh, it's a compiler, right? It's like a compiler, and compilers work in stages. It's also, we also call it a pipeline. You first generate, like load the outlines, convert them to quadratic, optimize them, auto hint it, add the G sub G pod. It just goes through stages. And it's like building source code. Like the first time you build a large source code, it takes a while, but it's very desirable that edit rebuild cycle be sped up. To do that, you want to be able to break this compilation pipeline into small pieces that, and then you want to be able to cache the intermediate parts, and so you can only rebuild things that changed. All of this would be easy if we have a very fast way to read and write things, any pieces of fonts. But then again, XML isn't that read and write fast, and Python pickle objects aren't either. Flat buffers so also solve that problem as an intermediate representation of the font table. So like the font table has CMAP, we will have a schema for CMAP in flat buffers, not to ship it in a binary to rasterizer, but just to enable creating it and reading and writing it. And then at the last step only, we need to compile it to the, convert it to the binary OTF format. And then when we do that, so when we create this intermediate flat buffer representation of the binary font tables, or any of these other formats, it might prove to be fast enough to access at runtime that we might choose to use it as a font format by itself without having to go to binary OTF any longer. So that's the basically the better ergonomics aspect. So I'm suggesting that we stop and sharpen our tools and tool set and reduce the pain of modifying the font format before moving forward. So that was part 2, and I said it will be quick. Part 3 is my favorite. And should we take another 3-minute break and start at the hour? Let's do that, yeah. And then maybe Peter can catch up. Okay, is audio good again? Okay. Hoping to finish earlier, not use the full 3 hours, but 30 minutes. Okay, I want to tell a story here. Let me load my notes. Okay, let's start like this. So, as I said, well, Nastali, the Cascading Arabic, we keep talking about it, and people have tried to address that many different ways and times. Everything I'm talking about, it is not Arabic specific or Nastaliq specific. I use Arabic and Nastaliq as an example of things we need to be able to do and we want to do. So here's the story. A font like Noto Nastaliq or any other uh, complicated calligraphy like font has a lot of what we call contextual rules, a lot of things that say, oh, if you saw this glyph followed by this glyph and this glyph in the middle, then change this one to this alternate form. Like a lot of this contextual. The way designers write this, you can think of them as regular expressions for the developers. But basically, when we are applying this, when we are rendering text, when we are shaping text, essentially we have to read these rules one by one from the font and go walk over the input buffer and see if the rule applies. So most of the open type G sub GPOS lookup types try to speed this up by fanning out based on the current glyph in the buffer. So you start walking over the buffer, you look at the current glyph, using a coverage table as we talked about, you decide which payload to apply. And then so you fan out based on the first glyph. But for example, if this is a ligation, all of the ligatures starting with the same first glyph will be listed here, and then you have to check each of them one by one. This is really slow. When we get to these more complex cases, like the chain context format 3, for example, it was complicated enough that some people designing it thought they can forego this fanning effect. So there's actually, well, there was an extra level of indirection. Some of the other lookups can specify multiple substitutions, whereas this one only encodes one rule. So the end result is that if your font has 100 rules, you have to have 100 lookups, and it means you have to walk over the buffer 100 times, and this really kills performance. So Martin Hoskin and I wanted to fix this. And from here, I'm going to show you where you get, and if you keep pushing the design, because it leads to somewhere really interesting. So as I said, if this part of the talk is basically putting back computer science into font file format design. Because when font file formats were designed in the 80s, computer scientists designed them. And you saw a state machine, you saw stack machines, you saw register machines, and then over the next 3 decades, we got to this point where it's a bunch of data fields and there's no science in it. And the open type layout, for example, G sub GPOS, reflects the way the designer thinks of the font, not how the computer desires the font to be. It's the computer, the interpreter, the font using software has to read these data fields and decide what to do with it. What I show is that it's much more natural to let the font tell the computer what to do. So that's what I'm getting down to. So if a computer scientist wants to design this, you say, okay, you have a buffer. You look at the current glyph. So the same coverage table, or it can be a coverage class combined, and you fan out based on that one. But you don't stop there and list all of them. You also then look at the next glyph and say, okay, what's the next glyph? And you fan out from there, right? So at every point, never you have to walk over 100 rules and see which one applies. You just fan out. And those with the computer science background know that this is simply called a try data structure. And now when you encode this try in the file, it will be, well, jump from here to here or here, and then from here to here or here. So a lot of offsets and jumping. Now, so you start from here and then you walk one glyph, two glyph, and you see, oh, failed. You just move the buffer forward and start from the top again. Now, this is an acyclic graph. If you allow the offsets to be negative as well, so you don't have to just go forward and you can jump backward as well, you have recreated finite state automata, which, again, as the computer scientists know, is equivalent in expressiveness to regular expressions, which is where we started. The designers think in regular expression terms, even if they don't know it. Like the languages they use to specify this look like sub G with, I don't know the syntax, like by G dot alt or something. Well, this is code, even if you don't know it, right? So we get to the finite state automata here. And then since we have to produce output, there are operations you need to do, like a substitute or a move. And again, as I said, if you allow jumping back, then you have a full state machine, a state machine. And of course, that's how Apple designed their solution back in the 80s, 90s, early 90s, I think. That's what the Apple advanced technology is called. The Mort table did. Indeed, the Mort table actually used offsets from one state to the next state. Now, another thing that this provides for us is that when we started here, you would start matching one rule or all of the rules now. You match, you fan out based on the first glyph, and then you fan out based on the second, and eventually you see that there's no rule matching. You would then have to advance the buffer forward and start this search again. But then again, the computer scientists know that we can do some analysis on this state machine at compile time and decide that when you saw a no match, you don't have to go and start matching the next glyph from scratch. You can pre-compute what state you would end up with the next glyph, because you already saw the next glyph. So you can do some pre-processing on the state machine to speed up matching. So the end result is that, well, you are in some state and you check some things, and depending on that, choose where to jump. And then you check some things, and depending on the results, you choose where to jump. And then you let the compiler put this in a serialized order. Well, what I want you to realize is that you just produced code. This is like machine code for a imaginary open type layout machine. Right? So now this is what Martin Hoskin and I proposed back in 2016 called complex contextuals. And it solves many of the limitations of OpenType layout. But I'm not proposing this anymore, because to implement this, we would need to build tooling to read the regular expressions, build this state machine, then use some state machine compiler to optimize it and reduce it and do things to it. Then we need to specify a file format about how to encode this, and then generate that encoding. And then on the shaper side, at consumption time, we need to parse that and understand it and interpret it. Well, this is just bizarre, because doing that, reading this thing, optimizing it, putting it in a binary order that jumps around is what compilers do. So instead of designing formats that have to balance and anticipate the use cases and optimize for it, we should just let the compiler decide what to do. And if 10 years ago I said I want to put code in the font, people would have laughed, or 20 years ago. But first things first, we know that the fonts are Turing complete already. That's not the point. But it's just that the progression of web technology and computation in general, and sandboxing and isolation, has made it feasible to do that now. So essentially what I'm proposing is that we should just put WebAssembly inside the font. And so the font can decide the best optimized encoding for how to represent the particular case. So instead of constantly having to define a format 1 and a format 2, and then the explosion of the formats and sharing, we just use the regular compiler pipelines that have seen 40 years of optimization work go into them. So that's what I'm proposing, but I want to talk to the some specifics of how that will work. Felipe said, and the sorting of entries can be done. So Felipe, yeah, I mean, that becomes a compiler optimization. Everything becomes a compiler optimization. Okay, so first, to justify this more, to expand more on it, I want to draw some examples from the history of computation in general. Where do I start? Oh, first, let's talk about fonts. What are fonts? What do we have this object called a font? What is it? Well, a font only exists as an API to implement Unicode. Basically, if we didn't care about the text being readable to computers, that is copy pastable, searchable, then there wouldn't be a need for an object called a font in the way we know them now. You could just draw things or ship an image. That's how it started, right? The font exists as an API to implement Unicode. So Unicode crosses boundary here. And on the top is the application layer. Well, we have JavaScript, we have web apps, we have mobile apps, there's custom code, there's user code here. Underneath, we have moved to a static data representation. But that's not how it always was. If you look at Tech, Tech and Metafont, Tech and Metafont were really general computing, Turing complete computing at the font level. Metafont was not a font compiler, it was a rasterizer. The output of Metafont, the input of Metafont was code, Turing complete code. The output was a bitmap raster. The output wasn't TTF, it wasn't curves. It was used at rasterization time, although it was so slow. So 40 years ago, we had general computation at the font level. It never made the leap to become common at the web or application layer. And I'm fully convinced that the gap between professional typesetting and everyday reading, can be finally closed. And Take itself also wasn't just a document format, it was a full scale general programming language to build packages. So that's why to build on top. So you have latex and you have context. And so when we get to the question of Nastaliq, how we're going to solve Nastaliq, well, the SIL Graphite people, Martin Hoskins' team, have one way, one proposal, and then there's deco type, and then there's uh, digital hat or Nastaliq, anything. Again, when I say Nastaliq, that's just an example. And then in Iran, there's like probably another 5 implementation. There's so many different attempts, most proprietary except for graphite, to solve a problem. If we think font formats in the old way, we would have to pick a winner here and then specify it. That would be like tens of pages. Uh, I know because Martin wrote one. And then specify it and implement it and build fonts and then use it. But we shouldn't have to choose. We should just give an API such that people can compile graphite or decotype or digital hat or OpenType and ship it with their fonts if they choose to. Yeah, it's very similar to PostScript Type 3 fonts. Again, as I said, the 80s and early 90s saw computer science in fonts. It just dried up over time when we got to OpenType. And for 10, 20 years, it was considered that computability is a security risk, whereas if that was true, but it's a risk, the risk can also be studied and mitigated. So I just want to give you a look at how computation moved in this direction, and fonts just never did, and I think it's time to catch up. If you look at graphics, well, there was OpenGL 1 style, and it was a fixed pipeline. You had to specify your shape and then choose a color, a material. And then OpenGL 2 said, hey, let's introduce the shader language so you can write a shader, which is general purpose code. It's general purpose code. It's Turing complete. Well, maybe not, but it's general computation to a special machine, right? And then even that was not enough. It's basically the thinking is the GPUs can do so much more. Why limit what we allow the developers to use, the game developers to use? And then the next generation, you see something like Vulcan, which if the shader, OpenGL2 shading is similar to JavaScript. I'll talk about that in a second. But basically, you're shipping the source code to the shaper, to every client. So the client, the client's system, the OpenGL driver has to have a compiler to compile this to optimize machine code for the GPU. Then Vulkan said, well, that's stupid because a good compiler is really hard to build. And not every driver shouldn't have to have a full optimizing compiler. So Vulkan ships its shaders in binary formats and let the compiler do a lot of work upfront, and you just ship the output in a language called Spear V or Spear 5, I don't know which one, which is a portable GPU assembly language. So if you look at the web itself, originally we had HTML, CSS, static content, and then JavaScript appears. So already you are giving programmability to a third party, unknown, unsafe, untrusted actor. So that's not new in any way. Let's get beyond that. And then when Canvas was added, drawing became completely general purpose and up to the hand of the designer. And then ASM.js, Ask.js happened as a way to treat this, to use this mechanism to ship, to just compile your C code and ship it. And then eventually, well, Ask.js with WebGL, had programmability at the CPU and the GPU level. And then it also made the leap, and people said, hey, it's stupid that we are using JavaScript to ship basically what should be an assembly language. So the WebAssembly was designed as a portable assembly language. So you have a optimizing compiler, do a lot of work, produce this, you ship it, and then the client has to specialize this for the specific CPU they're running on, but otherwise that's a fast operation. So WASM and Web GPU is how the future of the current approach to how to do web apps. Same ideas. Even when you look at the servers, like computation in general, like 20 years ago, 25 years ago, when the internet started, you would get a IIS server on a Windows NT, or you get a Apache server on a Linux, and then if you rented servers, you will be sharing the same uh, server software with everyone else. Every time it needed to be updated, they have to update it, and you have to update your software. Then after that, so that was the static model. Then we get vServers, and virtualization appeared. So everybody gets to install their own desired operating system, and then basically the servers became these hypervisors that just orchestrate things, and you have virtual machines on top, and the client chooses what to run. And Docker appeared as a easier way to ship these contained systems, and well, WebAssembly surprisingly has leaped to, other than just being a thing for web apps, has become into what is called edge computing or edge computation. Uh, the idea is that since there's already implementations of WebAssembly that are contained and secure, then you can allow your web server to run code on your server devices at the edge of the internet. It has been optimized for that use case, so the resource requirements have been shrank down. Again, WebAssembly already has to address all the security aspects of untrusted computing. So all of those are already in place. You already can limit how much work that can do. You already decide what system resources it has access to. By default, there is no access. Anything you want that code to have access to, you have to provide to it from the host. So none of this is new. I haven't been reading the comments. Let me finish. We're almost done. And then even when we get to mobile apps, something like Flutter, Google Flutter is based on this idea that the app developers shouldn't even be bound by the app model that Apple provides or Google provides, and they can take their own app model and ship it everywhere. So that was the main pitch. And the way I see this work out is that first, we are not going to use this for everything. Like the web, this is one of the ways we make available to font designers. Most fonts still will be using fixed data formats, but if you choose to, you can ship WebAssembly with it that overrides the drawing, overrides the shaping, and then extending font format, instead of having to do this tedious byte specification and things, becomes more like web APIs. You just define well, web IDL, or you basically just define an API. For example, here's a shape API. I don't know. You just say, oh, shaping. It takes a buffer and a Unicode script, and then it returns the glyph array. That becomes your shape API, and then the implementation, Harfbuzz, Cortex, others implement plug into calling this into the WebAssembly module, and then the font developer writes this in C++ or Rust or TypeScript and generates, compiles it to WebAssembly, and that becomes the font. So we let all of the optimization work become a compiler issue that are not the font file formats concern. So in this sense, we are immortalizing the font format. It will be just a container. Fonts, the technology changes with the font, and the font format doesn't have to actively change all the time. Now, again, we can learn from Vulcan and OpenGL and the Kronos group in general. There can be modules and extensions, and then we can have a module manager, extension manager. For example, OpenType shaping becomes a module or extension you can use to say, oh, I'm using this model. Or you can have, yes, it's type 3, I already mentioned that. It's different, but yes, general computation. So you can have graphite or you can have decotype, and you just compile the existing shaping logic and ship it with your font. And yes, it's not for everybody. Not every font will use that, but the common modules like Google on Android or Apple on their platforms, they can say, oh, we have these specific modules available. You can just invoke them and use them without having to ship them. And then when a module becomes really popular, it can be added to the next version of the standard, so that can be assumed. That's exactly how the web evolved, exactly how the Vulcan OpenGL evolved. It just makes a lot of sense. You're turning the thing on its head. The font tells the host, move here and line here and draw here. So again, as I said, none of what I'm suggesting is new. It's applying computer science ideas to font formats. It was what was done in the 80s and 90s, then forgotten. I think it's time to bring it back, and we can close the gap between high quality typesetting and everyday reading. And oh, we have 2 minutes for questions. I'm surprised by my timing. Okay, let me see. Okay. Nemo says, I'm concerned about the implications for constraint standards such as PDFX of active fonts. Well, we are keeping some level. The activity is not like the random in PostScript. Like we still have a font is still modeled as a collection of glyphs, and the drawing of each glyph is constant, and we do not we enforce that. We don't provide much access from the outside world, so the font program can draw the glyph one way only. What we're doing is allowing the compiler to do any kind of sharing it wants. So we don't have to design better, more optimized format for how to encode glyph outlines for a full font. The compiler infrastructure does that. The font code just calls move to line 2 things. When you're converting this to PDF or something, it's still a glyph outline. You can write it out, you can distill an old school non-active font out of it. This is just a delivery format, a more compressed format. It doesn't change the basics of what a font is. A font is still a collection of glyph shapes referenced to by glyph ID. Okay, Felipe says, would that kind of thing bring new challenges to LibreFont's licensing? I'm sure there's not really. It's not different from how web apps work right now. Anyway, we're out of time. I'm out of breath. I just wanted to get the ideas out, and then we'll see where we can discuss this further. Pippin says being able to execute fonts on microcontrollers with additional virtual machine needed makes it harder. It doesn't have to be. You can actually compile the WebAssembly ahead of time to native code. This way, you can actually compile the, say, for example, platform developers like Android or iOS, you can compile Roboto, same compile chain. Instead of generating WebAssembly, you can generate native code for your microcontroller, then you have fonts that are natively compiled and fast. Okay, thank you everybody, and yeah, I'm excited to talk about this with whoever wants to. Cheers.